Hello. So you can see the screen, I suppose. Okay, so we'll just go over this quick problem and explain a little bit about how to tackle these sort of phase transition diagram, phase change diagram problems. So this is a problem from, it's from a Zoomdale book. It's my favorite book because it took AP Chem long ago, and this is how I learned. This is the first book where I learned all this stuff. Okay, so from this problem, it says a substance X has the following properties. So we're not going to be just using water because water is usually one we can use. But I guess right here, what we want to do is create the phase transition diagram similar to, I guess, similar to what is given as you can see here, for instance, this is phase transition of water, and you can see its temperature as a function of heat, or it can be as a function of time. I think some of them show time, perhaps. This is the phase diagram of P versus T. But we're just looking at heat versus temperature. So you can see as you heat something, this one's cooling. You can see because it's reversed from hotter temperatures to cooler. This is cooler to hotter, and you can see it's like ice, solid, and then ice plus water. You see it's ice plus water, then liquid water, then water plus steam, then steam. So basically here you have solid, you have a solid plus liquid, you have liquid, then you have liquid plus vapor, and then you have vapor. And so what's going on here is you have changes in temperature. So I'm just going to call it temp changes. So this is like heating. This is like where you might be heating. So these purple spots are just heating, and it's one phase. So you're only heating a solid. You're only heating a vapor or a liquid. And then I'm going to draw it in green. These are actually the equilibrium phase transitions. So right here, you can see this is solid liquid equilibrium. So you have solid and liquid, and they're in dynamic equilibrium. And you have VLE here, or vapor liquid equilibrium. I'll try to keep this video short. And these are dynamic equilibriums at a certain spot. Because I mean, it is shifting, I guess. So once you evaporate something completely, or once you melt something completely, then you're going to get just one phase. But you'll notice is these equilibriums all happen at a constant temperature. And so this is BP, or the boiling point, and this is your melting. Sorry, I circled the wrong thing. This is your melting point for water. And so during these phase transitions, they are isothermal. And you would use delta H fusion for melting or freezing, and you would use delta H vaporization for evaporation or condensation. Yeah, so hopefully that gives a little more background. I'm going to clear this diagram. Okay, so now you can see here, we're back to this diagram. And so we'll have something like heat on this axis, and we will have, just like Dr. Dodson mentioned, this is temperature. I am only recording this just because I think it's going to take a while. So the problem is asking us to plot these. This is not going to be to scale. It doesn't really matter, but you know that the curve is always going to look something like this. In this case, we see the fusion is smaller, so I guess this is not extremely to scale. Don't know if I can. Okay. So basically, what we need to do is assume going up, you stop a little, about, that looks like 5. You go up more. This is not to scale. And then you would have a longer line that's about 4 times the length because it's 20 versus 5. Then you keep going up. So, yes, in this case, we have this information given. So then this temperature right here would be negative 15 degrees Celsius because it's the melting point. And then you can see here, this would be 75 degrees Celsius because it's the boiling point. And that's how we plotted so far. And I said this distance is about 5 kilojoules per mole, and this is about 20 kilojoules per mole, like the whole length. I just undo those to give some more room. Okay, and then basically from that, we know this is solid. This is solid plus liquid. So I'm just going to say SLE, or just S plus L. This is liquid plus vapor, and then this is vapor. And then what you just need is, you know, that so anything at stage, I guess, 1, 2, 3, 4, 5. So 1, 3, 5 are heating, or if you go in the reverse direction, this is heating, and this is cooling. So it's heating, and you can see that basically we can use the equation delta mc delta T. Q equals mc delta T. You'll be using that equation, and then 2 and 4 are phase transitions. And you would be using Q equals mass times delta H fusion, or mass times delta H vaporization. And then you have these two equations right here. Sorry, I'm just moving these. Okay, so basically once you have these two equations, you are going to solve this. I guess we already drew this heating curve already, and saying start at negative 50 degrees Celsius. I just have that there, but that's irrelevant. So this is the heating curve. Okay, so once we have that, it's asking calculate the energy that must be removed to convert substance X from a gas at 100 degrees Celsius to a solid at negative 50 degrees Celsius. So it's saying you're removing energy. So I guess right here, if you're heating, you're adding energy. If you're heating, you require it, so it's endothermic. It's a positive sign. And then if you're cooling, you're losing energy, and it's exothermic. It's one of those things, like boiling water is actually endothermic, not exothermic. You think there's a lot of heat, but like you require heat to boil. So then once you have that, yeah, so now you're starting at 100 degrees Celsius. So that's somewhere like up here, maybe. You can see that 100 degrees Celsius, and you're trying to get it to solid. So now so you know this is a gas, even if they didn't tell you, you know it's gas. And then you're going to solid. Assume X has a polar mass. I think it's supposed to say molar mass. I don't know why it says polar mass. Molar mass. That's kind of weird. Molar mass of 75 grams per mole. So, what you need to do here is some things. So there's some unit conversions and all that. So I guess for 1, you would be using, so this C at 1, you would be using a C of solid because the specific heat capacity of the solid. For 2 or for 3, you'd be using it for the liquid, and for 5, you'd be using it of vapor, specific heat capacity of the vapor. Remember, the specific heat capacities vary. It varies based on phase or state. And then once you have that, you just need to solve this. So we're starting at 100 degrees. This is our start. And this is negative 50 is our end. And so we just kind of have to apportion this correctly. So all we need to do is okay, so 1, you just need to do 100 degrees to a phase transition. And our phase transition is at 75 degrees Celsius. This is our BP. We're going backwards. So basically, you have Q equals MC of vapor or gas, whatever they say. Oh, it says gas. So of gas, delta T. And then, it's just the mass is given here. Oh, you'll assume conservation of mass. Convert. So I guess you can use how much? I don't know if they gave me amount. I don't think that's relevant. So we can just use this. The C is 1.0 joules per grams per Celsius, and then delta T is 75, which is our final minus initial. The Q is going to be negative because it's exothermic. Unit analysis. C's cancel. G cancels with this. So this becomes joules per mole. So we have, you just need to check the units, and then it's like 75 times 1 times negative 25 is negative 1875 joules per mole, or negative 1.8. Using sig figs, correct sig figs, 1.8. Remember, there's a dot there. Kilojoules per mole. So then once we have this, we just do the same thing for the second step fragment. So right here is gas to gas plus liquid, or vapor plus liquid. And then the next transition, so you're just cooling it to your phase transition. Then you have a phase transition. So you can just call this cooling. Then you have phase transition of gas to liquid. You're going to convert all the gas to all the liquid. And this is in VOE, it's in the dynamic equilibrium. So there's vapor and liquid in equilibrium. That's the region. And this was in one phase. It was 100% gas. Here you have a mixture of gas and liquid in equilibrium. You go into more detail if you take like a materials class or like engineering or maybe like physics or more thermo. But this is basic, so then you have MC. So this is kind of weird because it's per mole mass. And this is also per mole. It's energy per mole. The units were weird for this, but so it's energy per mole and this was mass per mole. But it doesn't really matter because you're just doing a rate instead. So then for this one, you have MC. Sorry, I'm using the wrong equation. So you have M delta H fusion or vaporization, sorry. And then Q equals latent heat of vaporization, so you have to take the negative of it technically. So you have mass of 75 grams per mole conservation, and then you have delta H vaporization, which is should be given here, right here, 20 kilograms per mole. Remember, this is not vaporization, it's condensation, so you need a negative. Delta H fab, let's see. So right here, delta H fab equals negative delta H condensation, and delta H fusion equals negative delta H melting. Fusion, I guess, or sorry, that's not right. Delta H, like freezing. So this one you use for when you heat, and this is when you cool. It's just a sign difference. Okay, and then once you have that, then you can solve for this, and you get Q equals negative 150 kilojoules. So you would actually, sorry, those units didn't match up because you can see that's kilojoules per times grams over mole squared. That doesn't make sense. So basically, in this problem, we're assuming per mole basis. So it's already per mole in this case, so you didn't need an M, which is a little weird. But you should multiply an M when you, if you did have a mount, so negative 20, so it's just negative 20 kilojoules per mole. But you can multiply this if you want, sorry. You can multiply it, like, so if you were given an initial amount, let's assume that we wanted to do this with like 50 grams, then all we need to do is just take this 50 grams, convert it to moles, using the mole mass, and so you know 75.0 grams per mole, and you know this would be equal to like whatever 50 divided by 75 is 0.67 moles, and so if that was your basis, you just would need to multiply 0.67 moles, and you would get negative 1250, or with sig figs 1.3 you would get this 1300 kilojoules. And then remember they're all in kilojoules or on joules, keep it consistent. And then so you would multiply 0.67 moles and you would get negative 13 kilojoules. So you can do it that way. And that way you multiply the moles to get this. And then you would continue doing this. I'm not going to show it for all of it. So again, you're going to do, now you're all in liquid, 100% liquid. And then now you're just going to cool this liquid at, which is at, sorry, this should just say, just gas at the boiling point. So you're going to do 100% liquid at, now our temperature is at 75 degrees Celsius still. And then remember there was no temp change here. It's isothermal. And then now we're going from the liquid at 75 degrees Celsius to liquid at whatever the melting point is, negative 15. So now we just need to cool it all the way to negative 15 for the next transition. And this is cooling liquid in one phase. So now our temperature is just changing. You just need to do Q equals MC L delta T. I'm going to pause the recording and continue. Okay, so we recalculated here, it's like negative 17 kilojoules per mole, or around negative 11 kilojoules, and then you just need to do another phase transition, and there's no temperature change again here. This is at negative 15 degrees Celsius, or the melting point. A whole process in this one would be at 75 degrees Celsius, or the boiling point. Okay, and then right here you're doing completely liquid to solid transition, or the solid liquid equilibrium. And this is called, so this process right here, number 2, was condensation. And then this process is freezing. It would be called melting reverse. Or vaporization. This. So what you do here is, again, just Q equals whatever the, so sorry, there should be a negative there, negative M delta H fusion. So Q in this case would just be negative 5 kilojoules per mole. Look at your units, so it's 5.0 kilojoules per mole. So that's the answer. Or if you multiply 0.67, you get negative 3.3 kilojoules. And this is specifically for that, like 0.67 moles. And then the last one you need to do is yeah, so this last one you have is finally the cooling of the solid to a core solid. So from negative 15 degrees Celsius, which is the melting point, to negative 50. So all you need to do is Q equals negative sorry, it's not negative, because the delta T will take care of your sign. So this delta T will take care of your sign, so you don't have to worry about it for the cooling solid. So you just need negative M C S delta T, and then you have Q equals 75 grams per mole, and then you just look up there, and it's actually 3.0 joules per grams degrees Celsius, and then you just need to do -50 minus -15, so it becomes plus 15 degrees Celsius, and you get Q equals -7.875 or 7.9 kilojoules per mole. And then once you have this, you can once again times 0.67 for this just arbitrary problem. And then you get -5.3 with the correct sig figs, because all of them were 2. So then that's it for this problem. And that's how you would solve it. I always end up writing bigger, but you can see here in case you want to screenshot that. And that's how we do the heating curve for substance X. And we got from 100 degrees Celsius all the way to -50. As you can see right here. So we got to 100 to -50. And we went from a gas all the way to a solid. So, I mean, I think that helps. So you just need to like partition this out. So the questions just to ask yourself, I'm gonna keep this short, but phase, what is the initial phase? This is really hard to see. So you just need to ask yourself initial phase or state, and then the temperature at which it is at to the final phase and temperature. So you just need to ask yourself what processes happen, and then you'll probably have a combination of cooling or heating. So these require temperature changes. And you might have some phase transitions. It requires extra energy in these phase transitions to turn something like solid, break those bonds in order to make them like liquid or liquid bonds and make it into gas. So something like water would have a lot of hydrogen bonding, and you're trying to break the phase transitions are breaking IMFs basically, or forming. You're forming or breaking IMFs, and this is an isothermal conditions. No temperature changes are occurring. You're just changing the bonds, breaking or forming bonds of the molecules. In the bonds, but not like the actual bonds. It's not the bonds inside a molecule. They're intermolecular, so between molecules. So you're not breaking any chemicals bonds. Not intramolecular, but intermolecular. And then I think that was it. Cooling and heating, and then you have phase transitions. And also the cooling and heating is strictly more of like kinetic energy changes. You know, temperature and kinetic energy are proportional. So it's these changes. Whereas here, you're just breaking or forming IMFs. Yeah, so there we go. So you can like screenshot that if you want. Okay, and then once again, here's the first page. And then here's the second page. And then we'll just zoom out. And so we solve these problems, and you can try this with your problems as well.